Drinking salty water is pretty stupid. Just ask this guy.
The removal of salt from seawater is a very complex process known as desalination. This process produces pure water which can be used for drinking or industrial purposes, making use of a huge natural source of water.
Obviously, a huge worldwide problem lies in the form of drought and a lack of clean drinking water, so desalination will be a viable solution to a lot of countries in need.
The task we have in hand revolves around the design of a plant that takes the salt out of seawater by a large complex of heating, cooling, evaporating and condensing.
Do you understand?
Yes.
Yes, this probably does sound confusing, but just hold out for a bit. Hopefully we'll make some sense of it.
An example of where desalination could be used in real life could be in Kenya, which is an increasingly water-scarce yet coastal country. It is projected to have less than a quarter of the water it needs by 2025. A desalination plant of our size could provide over 65 tonnes of water per day, which could be massively beneficial for the large coastal city of Mombasa.
The first thing we did was look into making a process flow diagram, which is essentially a stripped down diagram showing the key components of the process and what happens in each part. The diagram here shows a variety of symbols such as the pumps, heaters and coolers, amongst lots of other more complex components, which you can learn about on a chemical engineering degree from the University of Sheffield.
The next part is to do a ridiculous amount of maths, calculating how much salty, pure and vaporised water goes through each stream. The main example could be the fact that however much water you put into the system must come out the other end. As well as the amount of water at each stage, we also need to take into account the amount of heat in each stage.
We were given some information before we started, so we didn't have to do all the work ourselves. Using these figures, we could work out the percentages of salt and water in each stream. To do this, we got down with a load of riveting mass balances. This is when you use the percentage of salt and water in a pipe to calculate the flow rate of the stream and, in turn, calculate percentages in other pipes.
Next, we calculated the heat duty for all 4 exchanges. This is the amount of heat exchanged in the heaters and coolers, so we can see how much money we're burning by running the entire process. A chemical engineer's worst nightmare.
Unfortunately, the money situation gets worse. We also have to consider pumping costs of getting the water out of the sea, as well as getting around all the machinery. A huge part of chemical engineering is in the efficiency. Again, this revolves around more mass. See a trend here?
As always though, alternative arrangements can be suggested in order to save money, thank God, such as providing one large pump to carry seawater to different parts of the system, to use as a natural coolant, for example.
The principle of desalination we have described in this video is thermal distillation, a process in which the water is boiled and the steam is collected, leaving the salt behind, but this requires a significant amount of energy.
There are alternative methods such as shock electrolysis, which is a desalination process that simultaneously purifies the water. A filter acts between an anode and a cathode which traps bacteria, and any remaining bacteria is destroyed by the electric current via the cathode. All in all, the entire process of desalination might be a costly one, but has the potential to save thousands of lives around the world, as well as making pure water more obtainable for worldwide industries. We hope you've learnt a thing or two because of this video, and whatever you do, don't be that guy.
Oi! Oi!